This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2018 AP Calculus exam, free response question BC6, namely, radius of convergence and interval of convergence. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. First, I'll discuss the three convergence possibilities related to a power series. I'll review the definitions of the radius of convergence of a power series and the interval of convergence of a power series. I'll discuss the endpoint possibilities for the interval of convergence. And then I'll present a few series and the radius of convergence and the interval of convergence for each. And finally, I'll use the ratio test to find the radius of convergence and interval of convergence for an infinite series. Oh, and I'll leave a few problems for you to try also. I'm going to assume that you've already studied a little bit about power series. And in the power series you might have already considered the set of values of x for which the series is convergent turns out to be an interval. And the interval is either finite, an infinite interval, or a collapsed interval, for example, just the value 0. This theorem formalizes this general observation. For a given power series, there are only three possibilities concerning convergence. The series converges only when x equals a, the series converges for all x, or there is a positive number r such that the series converges if the distance between x and a is less than r, and diverges if the distance is greater than r. Let's take a closer look at this theorem and add a few definitions. The number r is called the radius of convergence of the power series. And by convention, the radius of convergence is r equals 0 in case 1, and r equal infinity in case 2. The interval of convergence of a power series is the interval that consists of all values of x for which the series converges. So let's apply this definition to the three cases in the theorem. In case 1, the interval consists of a single number, a. In case 2, the interval is minus infinity to plus infinity. In case 3, we can rewrite the inequality using interval notation. When x is an endpoint of the interval, that is x equal a plus or minus r, anything can happen. The series might converge at one or both endpoints, or it might diverge at both endpoints. Therefore, in case 3, there are four possibilities for the interval of convergence. This situation, case 3, is illustrated in this figure. This is a visualization of the interval of convergence. The series converges for x in this interval and diverges for x in either of these two intervals. And we need to check the endpoints separately for convergence or divergence. Here are a few examples of power series and the radius of convergence and the interval of convergence for each. And you might recognize some of these series. In the first example, the radius of convergence is 1, and the interval of convergence is minus 1 to plus 1, open at both endpoints. You might recognize this as the geometric series. In example 2, the interval of convergence is a single value, minus 1/3. In example 3, the interval of convergence is the interval 3 to 5, closed at 3, open at 5. And you probably recognize example 4 as the Maclaurin series for e to the x. Here, the interval of convergence is all real numbers. So, how do we determine the radius of convergence and then the interval of convergence for a power series? In general, we can use the ratio test, or sometimes the root test. However, remember that both of these tests are inconclusive when x is an endpoint of the interval of convergence. The endpoints have to be checked using some other method. Let's try an example in great detail. Let's see if we can find the radius of convergence and interval of convergence of this power series. Let a sub n be a term in the series, and consider the quotient for the ratio test. I wrote a sub n plus 1 divided by a sub n, simplified, and used a property of absolute value to arrive at this expression. Next, I evaluated the limit of this ratio, and looking at the fraction inside the square root, multiply the numerator and the denominator by 1 in a convenient form, 1 over n over 1 over n. And this limit is 4 times the absolute value of x. By the ratio test, the series converges if 4 times the absolute value of x is less than 1, and diverges if 4 times the absolute value of x is greater than 1. Or, another way to write this, the series converges if the absolute value of x is less than 1/4, and diverges if the absolute value of x is greater than 1/4. This means the radius of convergence is r equal 1/4. Now, this might be easier to see if we use a equals 0 in the inequalities. For example, we could write the series converges if the absolute value of x minus 0 is less than 1/4, and diverges if the absolute value of x minus 0 is greater than 1/4. In any case, we now know that the series converges for x in this interval. Next, we need to test the endpoints of the interval. For x equal minus 1/4, the series looks like this. And I recognize this as a p-series, with p equal to 1/2, which is less than 1. So the series diverges. For x equal to 1/4, the series looks like this. And with a little bit of work, I can see that the series converges by the alternating series test. So the interval of convergence is minus 1/4 open to 1/4 closed. Here's how I can use technology to solve part of this problem. Using the TI-Nspire, I defined the nth term of the series in terms of n and x. And then I simply found the absolute value of the quotient of two consecutive terms, a sub n plus 1 divided by a sub n. Note that since I did not specify n is greater than 0, the terms n and n plus 1 remain inside the absolute value symbol. I added another command in which I specified n is greater than 0. Note the slight difference in the output. Now I need to evaluate the limit of this ratio. We know that the series converges when this limit is less than 1. And we can solve this inequality for a more explicit interval. And we can now see that the radius of convergence is r equal 1/4. To complete the solution, we need to check the endpoints of the interval. So using the TI-Nspire, I tried to write and simplify the power series when x is equal to minus 1/4 and when x is equal to plus 1/4. My hope is that I'll be able to identify these series, know quickly whether they converge or diverge, or at least compare the result to a known series. And often the TI-Nspire will actually be able to evaluate the series. When x equals minus 1/4, the TI-Nspire returns the sum of the series as infinity. This is an indication that the series diverges. Now, I can't justify this yet, but looking at some of the terms of the series, I can see that it's a p-series with p equal to 1/2. When x equals plus 1/4, the series is alternating, and it does indeed converge by the alternating series test. And here are a few terms of this series. Here are a few more problems for you to consider. Find the radius of convergence and the interval of convergence of each series. I hope this video provides some insight into finding the radius of convergence and the interval of convergence of a power series, a few AP Calculus type problems, and the use of technology to solve and explore these types of problems. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.